The main idea in this course, the idea that's going to pull everything together, is the idea of mathematical modeling by functions and equations. Okay, now what do we mean by mathematical modeling? Let me show you actually the first situation you're going to see. I have here a uniform cylinder. There's a hole near the bottom of the cylinder, and I got to find that hole because I need to put my finger over it. There's a hole right here. There's a scale along the side by which we can measure the depth of the water above the hole. Now, I'm going to pour water into this cylinder. Okay, there's plenty of water, and you can see the level of the water. Now, when I let go of the hole, water is going to begin flowing out of the cylinder, and you'll be able to see the level of the water decrease as the water flows out. So let's see what happens. Okay, here we go. There's the water spraying right out at you. I'm going to put the bottle down here to catch the water. And we see how the water level is changing. The water is going down. You're not going to be able to read this scale, but you'll get either simulated data or you can do this experiment yourself using a 2 or 3 liter bottle instead of this cylinder and measuring the depth change along the uniform part of the bottle. You can get some very good data. Now what we're wanting to measure is the depth versus the clock time. One way to do that is to stop or to look at a watch or some timing device every time the depth changes by a centimeter or 2 centimeters or 3 centimeters or something like that. Okay, so we get the depth versus the time reading on the clock, and from that we'll be able to determine how the depth changes with respect to time. Now this is one modeling problem, and this one actually is something we can model very, very precisely by a quadratic function. In the process of modeling this phenomenon here, you'll get a good review of simultaneous linear equations and the quadratic formula and the graphs of parabolas that you had that you studied in Algebra 2, or should have studied in Algebra 2. Most people study those topics in Algebra 2, although it's not always covered. Okay, so there's one situation. Now here's another situation. I love Christmas tree ornaments. So I've got these 2 ornaments here, okay? And a nice, attractive, concrete-filled glass ornaments. And really, of course, we don't hang these in trees because they're pretty heavy. If you drop this in somebody from 30 feet, you'll kill them. Okay, now these are pretty heavy, okay? It doesn't feel good, okay? Just crack the glass. That was smart. Okay, well, now that I know that my head's harder than the glass, no surprise there. Now, these are pretty big. They're 3 inches in diameter. But of course, I've got a bigger one here. Okay, this is 4 inches in diameter. Now, you're probably going to believe me when I tell you that this one is about twice as heavy as this one. Actually, it should be just a little bit more than twice as heavy. And the reasons for that will become apparent later in the course. Does that mean that it's got twice the diameter? It's twice as heavy. Does it have to have twice the diameter? Well, no, it doesn't have twice the diameter. If I put 2 of these together, they're a lot wider than this one, okay? See if I can hold these so you can see that. We see clearly that the 2 small ones are a lot wider than the big one, so that the big one does not have twice the diameter of the small one, although it has twice the mass. And you might ask, how can that be? Is that reasonable? Is that the way things should be in the universe? Well, there's this idea of scaling. And in the process of studying the idea of scaling, we talk about power functions. Power functions are a very important class of functions. And we develop the algebra and the other details that we need to graph and analyze power functions. Now I'm going to turn you around here a little bit and aim you at a computer monitor sitting all the way across the room. And angles aren't real good here, but I'm not going to take a lot of time to fix that. Okay, let me just try one thing here. And that's not working, so we're just going to live with that tilted angle. So just get used to being cockeyed here for a minute. There's the screen. Now I've had to walk around a little ways to get this, but what I have here is a graph. I've got a temperature probe sitting in hot water. This probe is attached by a wire to an interface that goes into the computer, and the computer is going to reveal the temperature. Okay? Now the temperature is coming along here. And we see the temperature moving right along. And I've made kind of an error in doing this, so I'm going to put a stop to this. I'm going to go back and I'm going to set this up again. I meant to set this up for 2 minutes so that we'd be able to see it well. And here we go. Okay, now we see the temperature, the blue line moving across the screen, and the temperature is remaining pretty constant because, of course, the thermal probe is in warm water. Now there are little fluctuations in the temperature, but the progress is pretty much straight across the screen. If I take the temperature probe out and dry it off very quickly, we're going to see the temperature fairly rapidly drop toward room temperature. But of course, the closer the temperature gets to room temperature, the less quickly the temperature is going to drop. Now room temperature is down around here someplace. So let's just watch how the system behaves as the temperature comes to its equilibrium temperature. We can certainly see the curvature that's beginning to appear in the graph and how the temperature comes down rapidly at first but levels off more and more as it approaches room temperature. Now the room temperature that it's approaching is what we call an asymptote. And the function that we get here is called an exponential function. And we can model this phenomenon using exponential functions.